Hello viewers and welcome to another episode of Space Science with Python. In today's session we are concluding the support vector machine part. So the last time we focused a little bit on the support vector machine. We considered a binary classification between the X class and what I called the non-X class. We did some grid search, parameterization, or finding the best parameters and some kind of fine-tuning. And today I would like to conclude it by showing that support vector machines are also able to do multi-class classification tasks. And well, we talked a little bit about the theory of support vector machines, that you're drawing some kind of hyperplane in a multidimensional space to separate two linearly separable data sets. But we can also have some kind of multi-class hyperplanes for different classes, like not only some A and B class, but also C, D, and so on. And there are different methods how to do it. And scikit-learn also has these capabilities. And we will talk a little bit first about the theory, how multi-class support vector machines work. So let's move to my amazing drawing skills, and let's draw some classes. This time we are drawing 3 classes in some 2-dimensional space. So let's make some small red crosses here on the left hand side. Then let's have a second class, like, I don't know, a blue class like this. And now our third class, maybe small triangles. So of course, in our case with spectra data, this is of course not 2-dimensional, but we work there in a multi-dimensional space, but the idea still applies here. Now if we consider one of the last videos where we're talking about hyperplanes, we were mostly talking about drawing some kind of plane between two data sets that have the maximum margin between both data sets. Okay, here it's not symmetric, but mathematically it's symmetric, but here it's a little bit limited by my drawing skills. And in a multi-class classification, it also works like this. So we create different hyperplanes between the different data sets. But the point is how the algorithm sees the data, or how the algorithm considers the data for creating the hyperplane. So one is the so-called the one versus the rest algorithm. It's something like, let me write it here, the top, one versus the rest. And this one is quite straightforward. So it considers, for example, one data set here, and it compares or considers everything else as the counter class. So in this case, it will take these data as one data set. So one class versus the others. In such a case, the hyperplane would be drawn based on both data sets. So we need a maximum margin between these the red data and the blue and the yellow one. So it would maybe look something like this, for example. So maximum hyperplane here with also good distance to the blue ones. This is the first method, and then it applies also does the same thing for the others. So it takes then the blue data set as one class and the red and the yellow one as the counter class. So it draws then another line which may look like this. And then of course the final one, the yellow versus the rest, which looks like this. So you have then different hyperplanes drawn that are then, let's say, being entangled, merged together into one classifier when there are new unknown data points. So this is the one method, the one versus rest, and the other one, 4% battery, I should hurry up. And the other one is the so-called 1 versus 1. And in this case, it takes, let's say, the red data set and the yellow one and only creates a hyperplane between them. Then it takes the red and the blue one, and then the blue and the yellow one. So it ignores different classes. And this may look then like this, that we have a classifier that looks like this one between yellow and red. We have maybe this one here between yellow and blue. And then finally, what's missing? No, that's separate. Yeah, of course. And of course we have blue and red, which looks then like this. So the hyperplane even goes through the yellow data because the algorithm doesn't care about the other data. And then we have also here some kind of different shape for a classifier. And scikit-learn provides all methods. So yeah, this kind of one versus one or one versus rest. And yeah, we will take only one method. So yeah, I will provide a link into the description where you see in scikit-learn the different support vector machine functions and classes, how to instantiate them, and with what kind of arguments you can enforce the one method or the other one. There also, yeah, of course, you can then also apply kernel tricks and whatsoever. This is quite huge and complex. Okay, so I think we can move now to our notebook. And in our notebook, we can now, yeah, conduct our machine learning experiment with the multi-class support vector machine. So the script is, of course, again on GitHub. So feel free to download it or directly call it in Google Colab. And you see, I already executed the first cells here. Basically, you're familiar with it. Some import, calling, assessing the Google Drive data, the level 0, level 1, and level 2 data. We need, of course, only the level 2 data that is read here. We take the spectra data and the corresponding classes from the main group, and then we do a stratified shuffle split in this cell. So the next thing is, of course, we need to compute the weights of the different classes, because the classes they have different they're not equally present in the data set, in the training and in the validation test set. I think, if I recall it correctly, I think the C class is the most frequent one, then the S, then X, and others. So we have to compute the weights to let the algorithm later know that not every class is equally represented. Last time we did this by simply computing a float for one of the classes, but today we have several classes. We have 4 classes, so we need to create something like a dictionary that stores the weights for each class. So what we do here, we are creating our empty dictionary, and then we are iterating through all classes. We use numpy.unique, and then from the Y train, so we get the C type, S type, X type, and the others. So only these 4. I could also hard code it, but yeah, let's take like this. And then we add something to the dictionary. We add the class. So the key is something like this, like the letter C or X or S or other. And the weight is, of course, we take the length of the training vector. So one has maybe 50 or 100 or 20. So we take the train, and then we take the inverse and then divide it again by the entire length. So for example, we have to do the correct weights depending on each class that is present in our data. So length of the Y train, we only take the ones from our asteroid type. And then we divide by the length of the entire class list. So let's see, compute it, and now we can print it out, the weight dictionary. And it didn't work. Okay, it did something wrong probably, or most likely. Yeah, sure, I should have, yeah, I think I did it wrong. This has to be divided by this. Yeah, I shouldn't have done this with the 1 divided by. It's a little bit too confusing, but there we are. These are our weights for C, for other, S, and X. Okay, so we will use that later for our classification algorithm. Of course, as last time, we take from scikit-learn, we will take some metrics. The one is the F1 score. Import F1 score, and a little bit clumsy today, and we need something which is called the make scorer. So we will create some kind of, let's say, costume scoring, but we'll get to this in a moment. Okay, so now we can create our parameter grid for our grid search. And here we can say, I don't know, I think I will upload a script which goes through the linear and RBF kernel. I would suggest to use only the RBF kernel today. And as you may remember, I think we computed until C value of 50 or so, and it was 50. Yeah, it varies a little bit based on the initial values. I would suggest to move the C value between 0 and maybe something like between 100 and 1000, and then maybe in 25 steps. And then our kernel is the RBF kernel. Okay. Yeah, and we can also say we take the linear kernel, but I think I will just upload this in the GitHub repository. Otherwise, the training will take some time, even in Colab. So let's set our classifier. We use the support vector machine function from, or the class from scikit-learn. And we, of course, initiate it with our weight dictionary. So it simply takes the weight dictionary. And then, of course, we need to scale our data accordingly. So we have to call the pre-processing part and then the standard scaler. And then we directly fit it with the xtrain. And then, of course, we need to scale our xtrain data accordingly. So scalar.transform, and this transformer applies also later to the test data set. So it's very important to use the scalar only for the training data. Never scale the data based on all data. Otherwise, you get some kind of information leak from the testing data or validation data into your train data. And this will bias also your algorithm, and you do not want that. So to be 100% unbiased. Here we are then setting here our grid search CV cross-validation algorithm. We take the support vector machine in there, our parameter grid, and then also our scoring. So we create a scorer. Score average is weighted, and then verbose 3, and cross validation maybe again 5. Okay, and now we can simply run the script and conduct the fitting. So we just fit it on the xtrain scaled data with the corresponding labels ytrain, and let's go. Okay, we are back, and I totally forgot to mention one thing before we continue. So you have to know that the F1 scorer in scikit-learn, it always computes the score for each individual class. We have our multi-class. We would like to see the F1 score of the entire classifier, so we have to consider all individual scores and weight out our or average our scores. So that's the reason why I was writing it here, so that we have a single score written down there. We can actually maybe recompute it, because I played a little bit around with the linear kernel, but it took a little bit too much time, and I just didn't want to wait, and also the performance is way worse. So let's see if I just retrain this one here. That should be quite fast. And there you see that, it actually spawns just a value error. It says the target is multiclass, but the average is binary. So it always, I could have written that it's like X and non-X, C and non-C, as others and non-others, to compute the F1 score for each classifier. But per default, it always expects a binary case. So here we have to create an average, and then we get our final score. Now, talking about our final classifier, we can then also assign our final classifier. I just saw that I did a small typo, so it's not CLF, it's LCF, but yeah, that's fine, I'd say. So the best estimator, and then with final CLF, and then pressing a dot. Yeah, there we have, of course, our all attributes, the coefficients, the decision function. Okay, get parameters, for example. Let's see what we have. We have here our C parameter. Actually, it's at 1, which is quite surprising, because during the testing, it was always at around 10 or 5. So now it's at 1. Yeah. Well, you see all the values are very close to each other. So yeah, we don't see a huge improvement with varying C sizes. So that's fair. Let's live with that. And that's our final classifier. Try again also the linear kernel. You can also try the polynomial kernel. You can also do more feature engineering with the spectra. But I would say for such a simple case, this is quite a fair result and also performance. So now let's work with the test data. We take the scalar again and transform our test data. So there we are. And then, of course, we compute our y-test prediction, where we take the final clf.predict and take the scaled test data. So there we are. And then we have our classes from our training, from our initial, from our, let's say, from our expectation array. So the y-test, and now we have the prediction. And now we can do the fancy metric stuff we know from last time. We can again compute or visualize here the confusion matrix. I would suggest let's stick only with the F1 score, and let's compute and also visualize this time the confusion matrix. So small recap, confusion matrix. You just take the y-test and y-test prediction. Of course, you take also the labels here. So let's say C S X and other. I think this order was the correct one. So now we can print it out as you saw it last time. Yeah, it's like this, a 4x4 matrix. But now we can even use matplotlib to visualize it in a more fancy way. Pyplot. And then we need from sklearn dot metrics. I think there's also something called plot confusion matrix, right? Yep, there we are. So now we can say plot. I don't know if you even need matplotlib for this. Let's try it out without it. But I think I need to show it, right? But yeah, let's try it out here live. So plot confusion matrix. Well, autocomplete is never there when you need it. Final CLF. X test scaled. Y test. And then let's print out. Yeah, it works even without matplotlib. Oh, it's even deprecated and will be removed in the future. Okay, that's good to know. So you can work with it as long as it does. That's good to know. Maybe I should check whether there is a new function or whether it has been removed completely. So there we are. So this is our confusion matrix, and you see even with the eye, well, the performance is quite good. Yeah, it's a little bit suspicious that the testing data fits so nice, but yeah, maybe our data is just perfectly linearly separable. So yeah, for the sake of completion, let's compute also the F1 score, where we simply call scikit-learn.metrics F1 score. I think I even imported it, so I think I don't need to write this whole thing. F1 score, y test, and y underscore test prediction. Of course, multiclass. So again, the average is weighted. Yep. And then let's maybe round it to 3 digits. And then let's also, come on, weighted. And then maybe, round it to 3 values. And then we can print the F1 score. And there we are, F1 score of around 95 or 96%. I would say this is quite a fair result, considering that we have this small tutorial videos of only like 30 minutes or so, and we had now 3 videos about support vector machines, so in total, 1.5 hours of working time for such a nice F1 score. I think we can be quite proud about it. Of course, you can now do data engineering and so on to squeeze some more percentage or points out of it, but yeah, for a simple classification tool, this is super fair. And I think with this video we conclude the support vector machine part for now, for this project. The next time we will then finally go into Keras. Yeah, I also was thinking maybe to talk a little bit more about metrics like AUC and so on, the ROC. Maybe you can write me if you would like to see something more about metrics and how to store classifiers and talk about them. But maybe I will do this like an appendix after the whole project, talking about metrics, because otherwise it's a little bit too boring to work only with support vector machines. So yeah, let's continue with neural networks next time. We will not only build a classifier, we will also build something called autoencoder to get some idea how we can separate our data in some, let's say low dimensional space. So no spoilers now. If you want to learn about autoencoders, go ahead, and Keras and so on. My suggestion is that at least some kind of beginner level for the neural network and understanding would be quite beneficial. So I will not explain backpropagation or convolutional networks in detail. We will talk about architectures. We will talk about architectures like autoencoders and some kind of methods how to separate high dimensional data in smaller, lower dimensions. But my suggestion is get some understanding of Keras, of the basic functionalities. If you do not have it, don't worry. Especially the first videos, there will be quite simple neural networks, so it won't be magic for you, but you will not really maybe understand what's going on mathematically, because I think there are tons of nice material and content explaining neural networks and all these topics. So I will just simply use it and create some nice classifiers and other stuff with it. Okay, cool. I think let's conclude today's session. Let's call it a day. And I would say see you next week and enjoy some coding.